Okay, so today I'm going to present to you the first, sort of algorithm related to quantum computing, which was, the first algorithm also that was presented that sort of drawn a lot of people into quantum computing because it showed the power of quantum computing over the classical computing. And we will see in today's lecture. So the algorithm's name is Deutsch Josza algorithm. It wasn't, presented in the form that we are going to present it today, right in its, first offering. So the initial idea came in one of the paper of Diets, and then it was expanded by Deutsch Josza in 92, and then it was made into a form that we are going to discuss today in 1997 by other people, but it's still called Deutsch Josza algorithm. So this is an algorithm that shows the power of quantum computing in reducing the number of operations that are required to solve a problem. The problem that we will solve today, it's called Deutsch's problem. It's not that, practical problem that you might encounter in everyday computing life. But it's a problem that is sort of artificially made up, but it's a problem nevertheless. It's a computational problem. And if you do this problem on a classical computer, we will see that it takes exponentially many steps, exponentially many, number of steps to solve the problem exactly. But on a quantum computer, it can be exactly solved in just one step. So this shows an exponential speed up over the classical computers. Of course, it doesn't tell us that in general we can solve all the problem exponentially on a quantum computer than a classical computer, but it does tell us that there are some problems. There are some problems that can be solved much more efficiently on a quantum computer than on a classical computer. And by the way, since we can simulate all the classical gates using quantum mechanical gates, so everything and that can be done, in not much with not much of overhead. So if some problem can already be solved efficiently on a classical computer, it can be solved efficiently on a quantum computer anyway. So that is already available. But now with this problem, we will know that there are some problems that can definitely be solved exponentially faster on a quantum computer than a classical computer. And all the work and research that is going on into developing quantum algorithms right now is essentially discovering more and more of such problems that can be solved efficiently on a quantum computer than on a classical computer. And this algorithm, which is called Deutsch Josza algorithm, that's what we are going to do today. So I will start by explaining the problem, that what is the problem, and then I will talk a little bit about the classical, solution, which is obvious, and how many steps does it take. And then we will give the quantum mechanical circuit that can be used to solve it in sort of one execution. And then I will explain each part of the quantum circuit in detail because the main components of this algorithm, they're actually used in many other algorithms as well. So we will have to understand this algorithm not just to show that quantum computers can solve some problem efficiently, but also learn some of the techniques that will be used later on to analyze quantum algorithms, other quantum algorithms as well, which have practical applications also. So that's why this algorithm that we will study today, is simple, but still it's extremely useful. And that's why in most quantum computing courses, this is sort of the standard beginning problem to work with. So let me begin by sharing the screen. Okay, so we will solve Deutsch Josza problem and give a quantum algorithm for its solution. So let me make full screen. Okay. All right. So let's first describe the problem. So the problem is this, that you have a black box that implements a function f of x. That if you give some input x to this, you can get f of x on the output. And f of x is of only three types. It's either this, either f of x maps all possible combinations of the inputs to 0. Okay, so it's a function like this, that if x is input, and x input mean that x could be 0, or x could be 1, or x could be 2, all the way to capital N. And let me explain what this 0, 1, 2, etc. mean. Suppose the number of input lines are 1, 2, 3, 4, 5. Okay, so we have 5 input lines, and these are, binary inputs. So it means the input bit string can be either 0, 0, 0. So we can write it either like this, or we can just write a 0, because the 0 is a decimal representation of this binary bit string 0, 0, 0. Or the input can be like this. Maybe this is 0, this is 0, this is 0, this is 1. So this is this. So this is another combination. Then when I say that x is 0, it means all inputs are 0. When I say x is 1, it means all inputs are 0 except this one. Or maybe the input is like this, then I will label it 2. So this x is just a label essentially. The actual input is this, or this, or this, but this 0, 1, 2, etc. this is a label. Similarly, if the input is like this, then I will say that input label is 3. So all the way to this one, where this number would be 1 plus 2 plus 4 plus 1 plus 4, 2 plus 4 plus 8 plus 16, right? So this is 3 and 4, 7 and 8, 15 and 6, 31. So this x is 31, which is 2 power 5 minus 1. So this capital N is actually 2 power n minus 1, where n is the number of binary digits in the input. So the maximum n can go is 2 power n minus 1, because 2 power n corresponds to actually this 1 at the 6th decimal place. So then this number is 2 power 6, which is 32. And if this number is just before that in binary counting, so this is 31. So this n is 2 power n minus 1. Okay, so when I say that the input is anything either 0, 1, 2 all the way to n, what I mean actually is this, that the input is a binary string and the decimal value of the binary string would be 0, 1, 2 all the way to n. Now this first possibility for f of x is that all the outputs are 0. So this is, so f of x is either of this type, which means that f of x is either 0 for all x between 0 and n. So this is one possibility for f of x. So we are describing the problem. And then the second possibility is this, that f of x is 1 for all x, which means that the either f of x is 0 for all x or f of x is 1 for all x, means that f of x has a value 1 everywhere. And there's a third possibility in this black box, and that is that f of x is 0 for half inputs and it is 1 for other half. Let me explain. So f of x is of three types. Either it is 0 for all x, or it is 1 for all x, or it is 0 for half of the inputs and 1 for the other half of the input. So it is of this type. That, let's say it is 1 here, 0 here, 1 here, 0 here, and maybe 0 here. Or it can be of this type. Suppose we have 3-bit input. So then 0, 1, 2, 3, 4, 5, 6, 7. So these are the possible input to the 3-input circuit. So it could be 1 for inputs 0, 1, 2, 3, and it could be 0 for this. So the function is like this, that it is either it's 1 for half of the input and it is 0 for the other half. So when it could also be actually like this, that it could be 1 for these two, 0 for these two, and 1 for these two, 4, 5, and then 0 for this. So there are several possibilities for this f of x, but it has to conform to this thing that for half of the inputs, for example, 0, 1, and 4, 5, its value is 1, and for the other half, like 2 and 3, and 6 and 7, the value is 0. And you can think of any crazy combination, like, okay, you want it to be 0 for these three, and you want it to be 1 for this, and you want this to be 0, and then 1 for these three. You can choose any combination, but this is an f of x that for half of possible inputs, it should be 0, and for the other half, it should be 1. Which inputs doesn't matter. So it means that my f of x is of two types. That f of x is either a constant function or it is a balanced function. Constant means that f of x is either 0 or f of x is 1. And balanced means that f of x is 0 for half and 1 for the other half of the input. And the problem is now, Deutsch's problem is this. Answering this question, is f of x constant or balanced? Okay, so the problem is this: you have a black box given, and the black box has implemented a function f of x, which can be either a constant function or a balanced function. And your computational problem is this, that you want to find if f of x is constant or balanced, and you have access to this black box. You can give it different input and you will have access to the output. You don't know what f of x is, you have to find it, but you can give inputs to this black box and you can get outputs from this black box. So this thing actually is sometimes called an oracle. So an oracle is part of your algorithm or computational program that you can give input and it will give you output. Just like those wiser people in Greeks, I think those people were called oracles, and people would go to them and ask different questions, and they will tell them answer according to whatever their religious tradition was. So this name, I think, is just coming from there as well. So this is an oracle that you have access to, that you can send a query and it will give you response. But you don't know what is inside the oracle, or at least for the purpose of algorithm, you don't care what is inside. That's irrelevant. Okay, so anybody has any question about this problem? That what is the computational problem? Sameen, are you able to get what is the problem that we are solving? I don't have access to the chat box, but let's see if there's anything here. Okay, yes, sir, good. Anybody who doesn't get the idea of the Deutsch problem, that what the problem is, because it's really important to understand the problem. That you have a black box that implements two functions, which can give either a constant output, the same output for all inputs, and that same can only be 0 or 1, because we are talking about the binary inputs outputs. So binary output can either be 0 or 1, or it can be a constant balanced function that for half of the input, and it doesn't matter what half, for half of the input it is 0, and for the other half it is 1. And the problem is that you are given the black box, you have to find what f of x is. Okay, perfect. Now you understand the problem. Let's see what is the classical solution. So let me first talk about the classical solution, and then I will talk about the quantum mechanical solution. So classical solution. So classically, what you can do is give this black box different inputs. Okay. Sorry, I draw it like this, but actually this oracle has many inputs and there's only one output, not many output. It only needs one output. There's only one output because at the output it's either 0 or 1. So this f is a function. If I speak technically, it means it goes from a combination of n-bit combination of 0 and 1 and maps to 0 and 1, either 0 or 1. There's no tensor 2 or 3 or etc. It's only 0 or 1. Anyway, so it's a n to 1 mapping. So classical solution is this, that I mean, a naive way, that what I can do perhaps is give this as 0, 0 input and see what is the output. So you give this input. So I'm still using this cat notation, but we're just talking about classical solution. So you give it 0, 0, 0 and you record whatever the output. Suppose you get 0. Okay, then next time you give it another input and see what comes out. Suppose you get 0, right? Now but still I don't know if it is a constant or a balance, because next time if I do this, it can still give me 0. If still give me 0, okay, I will be happy that okay, it's probably going to be a constant, but I don't know, maybe on the next input I will get 1. So if I get 1, at least I can stop right here. Okay, I can stop here and say that's a balance, because I have only two options that I have to figure out, either constant or balanced. So if it is it has given me two outputs now I can stop, because it's not a constant. If it's not a constant, it's a balanced, I can stop. But let's work out the worst case scenario. So in the worst case, what could happen is this, that it is 0 even for here, and you keep going all the way until you reach so this is x0, this is x1, this is x2, this is x3. You might go all the way to input 7, and it will still give you 0, but at input 8 you get 1, because there are 16 possible inputs in this case, right? 0 to 15. So for 7 inputs I can get a 0, but at the 8th input I will know for sure that if it is a constant function or a balanced. So it means if there are n bits of inputs, I will need, in the worst case, at least 2 power n minus 1 divided by 2 number of queries. So this is the number of queries that you need classically to identify whether this is a constant or a balanced function. And you can see this q is, you forget this 1 because it's a small number, and this 2 power n minus 1, this is, so you need 2 power n minus 1 queries in the worst case to find out if function is constant or balanced. So this is exponential, right? This is exponential in n. And if this n number of inputs are, possible inputs are 100, it means you might need queries of the order of, 2 power 99 to know for sure that if it is a constant function or a balanced function. Okay, so you need exponentially many number of queries of this black box to find out if it is a constant or a balanced function. Any question about the classical algorithm? Yes, Ahmed Kirmani, please.
Sir, ये worst case scenario is 2 to the power n minus 1 divided by 2 या 2 to the power n minus 1?
Sorry, you are asking if the worst case is just 2 power n or it's 2 power n minus 1 divided by 2?
Yes, sir.
It's divided by 2 because for the half of the input. Oh, yeah, I get your point. There's a 0 already there. So yeah, this one doesn't matter. You're right. So it's 2 power n by 2. So if it is like 16 inputs, after 8th input, I will know.
Okay. Thank
you. But we work out these number of steps, imagining that this n is large, and then when we are working with large n, these constant small factor that doesn't matter. So, but you're right. It's 2 power n over 2. So. So everybody is okay that this requires exponentially many steps. So Abdullah, please.
Sir, can you hear me?
Gigi.
Sir, exact number of steps 2 power, for example, इस बोला 16 अगर इस केस में हमारे 16 total possibilities है हमारे inputs की, तो हमें at least 9 चाहिए होंगे at least ना कि to figure out if it is a constant function or a balanced function.
Right. Yes. So it should be. If you talk, in the exact sense, you're absolutely right that these are 8 input, and then I will need the 9th input. So which means that the in exact sense is 2 power n divided by 2 plus 1. But it's still of the order of 2 power n minus 1, because I can ignore this one if this n is 10. We are already talking about millions of inputs. 2 power 10 is of the order of millions. But you're absolutely right. If we talk, in exact senses plus, it should be 2 power n over 2 plus 1.
Okay, sir, I understand. Thank you.
Okay, perfect. So any other question or comments? If not, let me welcome you towards your first quantum algorithm. And let's now see quantum computer algorithm that was proposed by these people to solve this, artificially made up problem. And I will first give the algorithm, and of course, you might not see how it works. So then I will, explain its various parts. But before I do, let me talk about, in general, how quantum algorithms essentially works. So the major steps of many quantum algorithms are like this, that you of course has inputs that are different quantum states of qubits. And then in most of quantum algorithms, but not all, in most, we have a stage that prepare a superposition stage. it prepares a superposition of these inputs, of various combination of inputs. And then we usually have a stage that does some processing. Maybe you access some oracle as well in this stage, etc. And you might actually do it many times, maybe once, twice, or three times, or many more times. And then towards the end of the algorithm, we usually have a step which we call interference, where we interfere these states with themselves. And we then have these measurement stages after measurement, and then we get the outputs. So the idea is this, that we start with superposition state. So superposition is a state where all possible combinations of inputs, they are prepared in usually a uniform superposition, that all possible combination of bits are present. So you see, since this is a binary computer, when we measure it, the answer is just a binary string. So if we can prepare a state psi that has all, combinations of binary strings that are possible, it means whatever our answer is at the end, the answer is now already contained here. The only thing is this, that over in this stage, all answers are equally probable because they all have the same amplitude. And then what we do in this oracle part is, we do some processing, and then we do some interference and try to, so over here, we had an equal superposition of all possible state. And by this stage, our hope is that we reach a quantum state, which is something like this, that whatever we want in answer should have a higher probability amplitude, and whatever we don't want in answer should have lower probability amplitude, so that once we measure after this stage, our measurement result would be highly likely to collapse this state that we want in the answer. And you will understand it better, this workflow, when we analyze 3-4 quantum algorithms, that this is sort of the way quantum algorithms work. In the first step, we prepare a uniform superposition state that essentially includes all the answers that are possible. Answers are nothing but different combination of bit string, but all answers have equal probability. So essentially, we don't know anything about answer at this stage. But then we do some, processing, some oracle access, and this, you can include interference in this part as well sometime. But the idea of all of these two stages is to get to a state that goes from equal possibility of all bit string to more possibility of some bit string than the other, so that when we measure, we have a higher chance of measuring what we want in the answer. So this is called, this total part, you can say processing and interference are essentially the main parts of the quantum algorithms, and they vary from an algorithm to an algorithm. So let's now move on to this actual quantum algorithm, which is the Deutsch. And I'll actually come to this block diagram of quantum algorithms later on as well, a couple of times, to make this thing clear. So right now we are talking about algorithm. So Deutsch Josza algorithm is this, that what you do, you prepare bunch of qubits in 0 states, all of them in 0 state. And then you perform Hadamard gates on all of them independently, no control Hadamard, only independent Hadamard gates. So then we give this input of this Hadamard gates, which we also call Hadamard transform, to a phase oracle, and I will soon discuss what this phase oracle is. And then the output of this phase oracle is processed again, and we apply a Hadamard transform to this output again, which is nothing but individual Hadamard gate to each qubit. And then we measure each qubit, and whatever the measurement results are, we put them on classical bits. So in a classical register, we start from a quantum register and we put the results in a classical register. And based on these results, we will be able to tell what is f of x, if it is a constant or if it is a balanced function. So this is the algorithm, and let me now explain different parts of this algorithm in step by step. So let's start from here at this stage. So what I will do, and this is actually a very nice way of understanding quantum algorithms, that you start from the input, and let's call this state something, I don't know, psi naught, and then you work out the state of all qubits after each stage. So let's say the state of the qubits after Hadamard transform is psi1. We will work out what psi1 is. And once this psi1 is fed to this phase oracle, so this is called phase oracle. Right now it's just a name, but later on I'll show what it is. And then let's say the state of the quantum computer is psi2. And then we perform a Hadamard transform again, and let's say the state of quantum computer is psi3. And then after measurement, we have some output y. So this is not a classical, so y is something, I don't know, y naught, y1, yn minus 1. So this is, you know, the bit string. So let's say this is y naught, y1, yn minus 1. And let's now work out the state at each stage of this algorithm. So let's start from here. So psi naught is nothing but this state. So let's say this 0 is, so we now have to make a decision, okay? We have a bunch of qubits. So let's say qubit 1, qubit 2, and all the way to nth qubit. And we have to figure out, okay, if I write the state of a qubit here, does this go to the left side or does this go to the right side? So for now, let's make this choice that this one goes to the right side. So this is this one. Then this qubit. So this is the, you know, 0th qubit. So 0th qubit is on the right side. This is the first qubit. So it's actually first in the sense that let's call it actually 1th qubit. So this is the 1th qubit. So 1th comes here. Then the 2th comes here. And this one is the, you know, n minus 1th. So this is here. So this qubit refers to this topmost qubit that we have written in this circuit. So, and it means when we read off decimal numbers, we will have to then apply this notation. So this input state is just this 000 state. You can write it like this, or you can write it like this, or you can just write it like this. So there are, you know, several ways of writing this input stage. This is a labeled stage, that this 0 is actually not the state itself, but this is a labeled 0, which shows that the inputs of each qubit is 0. So this is the input at state 0, at this input stage. Any question about this thing? Perfect. So let's now go to the next stage. Let's see what happens after our Hadamard gates are applied to each of the qubit. Let's work that out. And let's call it psi1. So this means that Hadamard on this gate, on this qubit, Hadamard on this qubit, Hadamard this qubit, Hadamard 2. So all the qubits are being Hadamard. So this is nothing but 1 over square root 2, 0 plus 1. Similarly, the next one, 1 over 2, 0 plus 1, 1 over square root 2, 0 plus 1, 1 over square root 2, 0 plus 1. So all the qubits have gone to this, superposition state, which if you like, you can represent like this, plus, plus, all the way to plus. Anyway, we don't have to write it like this. Okay, so now let's see how we can, simplify it. I can write it in a short form like this. First of all, this 1 over square root 2, they're present in with all n qubits. So let me collect it together. So this becomes 2 power n square root. So actually it became 2 power square root and then whole power n, but I took n inside. And then let's see what is over here. So this 0 multiplies with this 0, 0, 0 of all states. So I get the first state as first term, all qubits 0. Then maybe this 0 into 0 into 0 into the last one from 1. So 0, 0, 0, all the way to 1. So then plus 0, 0, 0, 1, 0, and so on. And then perhaps the last term, all qubits in one state. So this is just, another way of writing it. And I can write it like this. So this capital N is now introduced to represent this 2 power small n. So this capital N is, the number of possible inputs. Now let's represent it with its label. So this 0, 0, 0, I can represent it with label 0. This 0, 0, 0, 1, I can represent it with label 1. 0, 0, 1, 0, I can represent it with label 2. And all the way to the last label being n minus 1. Okay. Good. So let's now collect it together. So I can write this sum as sum over x from 0 to n minus 1 as x. So this is my psi1 state. So this is actually exactly the uniform superposition that I was talking about, because this is a state now that has all possible input combination, but with amplitude 1. So psi1 is essentially nothing. If you plot it in terms of x for input 0, 1, 2, all the way to n minus 1, you have an amplitude, equal amplitude of all states, and amplitude is equal to 1 over n square root. So we have prepared a uniform superposition of all possible inputs. And this is the uniform superposition. So this is the superposition state is now going to be fed to this phase oracle. And that's what we have to talk about now. And this is actually perhaps initially, and also when you implement this most quantum algorithm, this is the tricky part. Even though in building algorithm, we sort of, put it under the carpet and try to skim over it. Okay, it doesn't matter. But this is actually the real meat of most algorithm, how to work out these oracles and how to, program these oracles into a quantum program. So now before I discuss phase oracle, let me now just talk about oracles in general, and then I will talk about phase oracle. So this oracle is, we can think of it a device or a circuit or an algorithm that has, so I'm not going to talk about in general term, and then I will specify to phase oracle. Let's suppose you have a black box or something that has this set of inputs. Let's say these are n inputs, and then whatever the input is x, it gives this input at the output, and let's say the output is still x. So These are n qubits, and they are going to the output as it is. So this is X input, this is the X output. But then it also has another set of inputs, let's say, and n in general is not equal to m. So there is some state, let's say y, and this output is changed so that the output over here is y plus some function f of x. And let's say I label this oracle as OF, where it implement this f of x. So this is, the general form of oracle, that there is one set of inputs that goes to the output as it is, and then there is another set of inputs that is XORed. So this is actually a modulo 2 addition with y. So it XORs a function f of x with the input y and gives this output over here. And now you can see one thing very quickly here, that implementing this circuit in quantum computer is not difficult, because you have this device called control X gate. This control X gate is essentially an oracle, if you think about it, because this input X is basically sent out at the output, and then this input Y is XORed with this X and given here. So this actually implements a function. Basically, if you think of this as an oracle, so this is a function f of x is equal to x, because this x is being XORed with this y. And we can then build, more complicated f of x with the combination of these control X gates. Anyway, so this type of oracle, by the way, is rarely used in most quantum algorithms. Mostly we are working with even a simpler version of this oracle. So this is, a general oracle that I have shown here. A simpler oracle is actually like this. So let's work with a simpler oracle. And it has this, n inputs that goes to n outputs. So this x goes here, and then for the m input, there is actually only one, and that also is tied to 0. And if you tie it to 0, basically whatever this OF is, so this is 0, so this output is then just f of x. Because if this is 0, so 0 plus f of x is just f of x. So using this bit general oracle, if you set this y to 0, this 0 plus f of x is just f of x. So we can get this function f of x right at the output using this oracle. So this, you can, if you wish, you can call it an amplitude oracle, because whatever f of x is here, it's appearing right over here. So the giant state, so input here is if we go with the previous notation that we just talked about, so the top one should come on the right and the bottom one to left. So the input is 0x and the output is f of x. So if you wish, you can call it sort of an amplitude oracle. And this is also the one that is not very commonly used. So the commonly used oracle is the oracle that we call phase oracle. So this phase oracle is a circuit like this that has n input that go to the output as it is. But then this input, which is sometimes called ancilia input or auxiliary input, this is tied to minus state. So which means the output here should be minus state XORed with f of x. And let's see what this is. So minus state XORed with f of x, and let's see, this minus is nothing but 1 over square root 2, 0 plus 1 XORed with f of x. So now this is equal to 1 over square root 2, 0 plus f of x plus 1, and this is modulo 2 addition f of x. And this is, there are two possibilities. If your f of x is 0, what would happen? This is 0, this is 0, so 0 plus 0 is 0, and 1 plus 0 is 0. And sorry, this should be a minus sign because this is a minus state. There should be minus sign. So if f of x is 0, you get 0 minus 1 as it is, which is nothing but minus state itself. And if f of x is 1, so 0 plus 1 is 1, and then 1 plus 1 is 0, modulo 2 I'm talking about. So 1 plus 1 is 0. So you get 1 ket minus 0 ket. And if I take negative sign common, then it becomes 0 ket minus 1 ket, but with a negative sign outside. So this becomes minus into minus. So this is nothing but, I can write it like minus 1 power f of x into minus state. So it means that this output is nothing but minus raised in multiplied by minus 1 power f of x. So since this f of x now goes to the power of minus 1, that's why this is called, phase oracle. Now I can write the total input output relation like this. So input is minus into x, and output is minus 1 power f of x minus into x. And since see, this is just a constant multiplier, you can think it with either this state or with this state. And this is, this is equivalent to thinking of it as minus 1 power f of x into x. So it means that if you now define, if you see, this is minus state, and at the output, this is still a minus state, and this phase part can simply go to this output x. So it means that my phase oracle, which sometimes people represent with symbol UF, is n input x, and at the output, it is minus 1 power f of x into x. And this minus 1 power f of x is nothing but, giving a minus sign to certain inputs and plus sign to certain other inputs, because minus 1 power f of x is either plus or minus. If f of x is 0, it is plus. If f of x is 1, it is 1. Let me recap, because it's a little bit confusing that why we are doing things this way. We started with this oracle because we can simulate it very easily with control x, because control x does nothing but XORs these inputs into this form. So this output is exactly y plus modulo f of x. So by different combinations of these CX gates, we can get this y plus different f of x. Now from this we can prepare either an amplitude oracle, in which case we can fix this input to 0, so that that function f of x just appears in the state f of x, or we can construct a phase oracle by tying this auxiliary input to minus state, because in that case the output of this auxiliary bit is -1 power f of x into minus itself. And this, if since these two states are multiplying, and this is a global phase, we can equally think of this phase with this x input. And now we have been able to implement a circuit like this, that this of course has this part as well, that there is this minus input going here, where there may be a lot of different cx's that are applying, but this is still minus, and the phase part is coming with this thing. Okay, and this is sort of a combination of design and science, design and art, to come up with different oracles that implement different functions. There is no general or generic way of me telling you, okay, there is this way you specify f of x and I will tell you this circuit is. Normally it's a combination of intuition and experience that you can construct different circuits to implement different f of x's. And let me now give you a couple of examples, because this is also part of your homework problem. So hopefully this will help you for your homework problem as well. So suppose you want to construct a phase oracle for this thing, that for state 0, 0, you might want minus sign. For state 0, 1, you want minus sign. And for state 1, 0 and for 1, 1, you want this thing. So this essentially, amounts to an f of x, which is 0 for these inputs and which is 1 for these inputs, because when this was 1, this -1 power 1 gave this minus sign. So let's see how I can, prepare this circuit. And for that, let's say these are two working inputs, and then this is the auxiliary input. And suppose you have been able to put this input to minus state, and that is very easy. If you have a qubit starting in 0 state, you want to convert into minus state, what you need to do, you first put an X gate and make it 1, and then you put a Hadamard gate, and the Hadamard will take this 1 to minus state. So, and this is the standard recipe in Qiskit of converting this 0 state into minus state, because in Qiskit each qubit starts in 0 state by default. So you can convert this 0 state to minus state like this. So suppose that this has been done. Now, if I look here, I have to make sure that when this input is 0, this left one, I get a minus sign. And it doesn't matter what's the input on the right side. So it means if this is, my, let me label it Q0, and this is Q1. So if this is Q0 bit and this is Q1 bit, so I need to get a minus sign independent of Q0, which is only dependent on Q1, because if Q1 is 0, I need to get minus. If Q1 is 1, I need to get a plus sign. So first of all, I don't have to do any operation with respect to Q0. Now with Q1, I want a minus sign when it is 0. If you just, put a C0 gate like this will actually work in reverse, because when this Q1 is 1, this will implement a C0 on this minus state and will give you a minus sign here, which is equivalent to putting a minus sign over there. So it means I first need to put an X gate. So I need to put an X gate, then put a control X gate, and then an X gate. So these two X gates will make sure that whatever Q1 was here is going to be the same over here, but this control X gate will act only when this Q1 is 0, because when Q1 is 0, this X makes it 1, and this 1 will make sure that this gets a bit X applied to this minus state, which will give a minus sign over here. So this minus, so or you can see that for these combinations of inputs, you will get a minus sign here and the same output here, which is equivalent to having a minus sign with this and the same in output over here. Everybody agrees how I got this circuit for this particular truth table? Yes, Ubaidullah, please go ahead.
सर एक ऑल्टरनेटिव हम इससे भी कर सकते हैं कि सर्किट इस तरह का कि एक कंट्रोल नॉट हुए Q1 और माइनस स्टेट के साथ और फिर माइनस स्टेट के आगे एक एक्स गेट हो, तो उससे वो भी पॉसिबल कॉम्बिनेशन है जिससे ये रिज़ल्ट हमारे पास आ सकता है कि 0 0 में नेगेटिव साइन आ जाए और 0 1 में भी नेगेटिव साइन आ जाए.
Sorry, can you please go ahead so I'll draw the circuit with you so that we can then analyze it.
Yes, sir.
You want, okay, so these are two, this is Q0, this is Q1, and this is this state. So what you want to do with Q0, Q1?
First have a control NOT gate between Q1 and minus.
Okay. And then
have an X gate on minus.
And an X gate over here. And that's it.
That's, yes.
Okay, let's see what happens. Okay. So if the input is 0 0, that your Q0 is 0 and Q1 is 0 again. So if this is 0 and so if this is 0, so this will make this will not do anything to this, but this minus state will be acted on by this X gate, and when this X acts, so this will give me a minus over here because this is a minus state, and if you change 0 to 1 and 1 to 0 with this X, you will see a minus sign over here, and let me put that minus sign with this input state. Now let's see what happens if this is 0 1. So if this is 0 and this is 1, and so this 1 will apply an X gate, and then there's another X gate, so X into X square is identity, so this 1 0 will come out as it is. And let's see what happens for 1 0. So if this is 1 and this is 0, again I will get a minus. And if this is 1 1, I will get. So let's see if it is the same truth table that we said we want. Now we wanted minus sign with 0 0 and 0 1. So this doesn't do that thing. It gives a minus sign with a different input. Okay. Bad, you agree?
हम सर ऊपर ज़रा कंपेयर कर लूँ मैं, एक से ऊपर कर सकते हैं स्क्रीन से?
Sure.
सर हम सेम नहीं है सर.
So I have a negative sign in front of 0 0 and 0 1. You have a negative sign in front of 0 0. Oh, yes. So you have the same. So then it's fine. So you can implement it with this circuit as well.
Okay, sir. Thank you.
Sir, ये circuit ज़्यादा efficient भी तो है because there's only one X gate being used.
So well, if you want to compute efficiency, there might be trouble because for this sign and this sign, so this is the Q1. So when this Q1 is 1, 2 X gates happened over here as well because this was an identity. So if you want to compute number of X gate, 1 happened here, and this X, and then 2 happened here and 1 here, and when this was 1 1, 2 gates happened over here. So this is like 2 3 4 5 6, so 6 times X gates are applied. So over here, so when this was 1 0, there were 2 X squares here, 2 X squares here, because this was 1 1, and these X are happening anyway. And so if you think about number of gates like this, they almost have, comparable efficiency, I would say. But there is, an added advantage with this design. When we go to more, complicated settings, it is better to keep this thing just being controlled by the top qubits, and don't do anything over here, because then you will have to figure out a way of canceling this X each time when you don't want anything done to this thing. So then you will be thinking in terms of controlling bits and in terms of controlled bit as well. But if you go with this design, this is easier to work with little bit, because you only think about, different combinations that you want to flip it. And for the other thing that you don't have to do anything. Okay.
Okay, sir.
All right. This, by the way, also has an equivalent symbol like this. So if a gate like this, this has this circle like this, that this actually means that this is being controlled with 0. So if input is 0, you apply this X gate. If input is 1, you don't apply it. So this is, the opposite of that dot on the control line. Okay. Now, I would actually like to go for a short break. But before I go, I just want to emphasize one point. In quantum mechanics and quantum computers, these things are equivalent. Okay, because this thing will give, if this is, fixed at the negative. So this gate will give a negative sign. So the 4 of these, if this is, X, so I can write this left side's output as minus into X, and the output of this, so this is minus and this is X. So output over here is minus into X. So even though this global phase is coming because of these, and this global phase is coming because of this, so the computationally speaking, this output and this output is the same. So just bear this thing in mind, and that's why, we were able to switch between this design and this design, because we can do this thing because computationally they are equivalent. So I think let's take a short break of 10 minutes, and then I will come to the next stage of this algorithm, that now let's work out this state psi 2 of this Deutsch Josza algorithm. Okay, so welcome back, and let me share the screen again. Perfect. तो हम जो है वो Deutsch Josza algorithm को डिस्कस कर रहे थे. So far we saw that our input was initialized to 0. Then after passing through Hadamard transform, we reach psi 1, which is the equal superposition of all possible combinations of input strings. And this is just, this thing. And now we are going to give this psi 1 as an input to this phase oracle. And that is actually where the difference between a classical and a quantum computer lies. And that's where a quantum computer derives its power. You see, this phase oracle essentially implements the function f of x. Of course, it implements it in -1 power f of x, but that's trivial difference. Now, classically, when we were trying to guess this function f of x, we were giving inputs on this, side one by one. Either input is 0, 0, 0, or input is 0, 0, 1, or input is 0, 0, 1, 0, and so on. But now we have prepared a state psi 1 that has all those possible inputs in a single superposition state. And we give that input as an input to this phase oracle. And the output psi 2 of this phase oracle, when we give this psi 1 as input, the output is So after phase oracle, psi 2 is 1 over n square root x goes from 0 to n minus 1 raised to power f of x into x. So you see this minus 1 power f of x is applied with every possible combination x. And that's where the quantum computer is drawing its power, that it can operate this phase oracle UF on each of the terms in the combination at once, because this UF, this comes on this x input, and then when this UF applies to any input x, this essentially gives this minus 1 power f of x into x, where I'm just putting this x, which means it goes from 0 to n minus 1. So this is the output of the phase oracle. And if you want to, picture this output, let me draw a graph for you. So this psi naught was 0, 0, 0, this thing. Actually, psi naught had all 0, and only this 0 state was present in psi naught, which was the input, because at input we had only this 0 state. But psi 1, after passing through Hadamard transform, it became 0, 1, 2, 3, all the way to n minus 1. All inputs are now present with a small amplitude 1 over n square root. And now once this psi 1 passed through phase oracle, it became like this. So it became psi 2, but psi 2 is this thing, that it's addition of all possible x, but some x are coming with negative sign and some x are coming with positive sign depending on f of x. So essentially the output after this is, some positive, some negative, and so on. This is what the phase part has done to it. And now we essentially do that, what we call interference, using again another Hadamard transform, because after phase oracle we have another Hadamard transform stage given by this, and let's do that. But before I apply Hadamard transform to this psi 2, which is this superposition state, let's do one thing in general. So let's talk about the Hadamard transform as in a general term, instead of just applying on a 0 state that we did previously. So before this, we just saw that Hadamard transform, essentially applying Hadamard gate to each of this 0 state was equal to this Hadamard on this 0, Hadamard on this 0, and so on, Hadamard to the last 0, and we got this linear superposition with positive amplitude 1 over n square root of x0 to n minus 1 x. This is what we got. But now let's say we want to find out what this Hadamard transform of a general state y looks like, where y could be 0, 1, 0 or 0, 0, 1, etc. So y is now a general state like this, n bit state. So Hadamard n minus 1, Hadamard on y n minus 2, all the way to the Hadamard to the last bit y naught. Okay, so let's work out this general Hadamard transform, which we will then apply to psi 2 that we had on at the end of the phase gate. Okay, so but before that, let's say what happens when Hadamard is applied to a general single qubit y naught. So this is, if you recall, Hadamard could be on 0 or 1, because this y naught is either 0 or 1. But if Hadamard applies to 0, this is nothing but 1 over square root 0 plus 1. And if Hadamard applied to 1, this is nothing but 0 minus 1. So I can write these, both of these output in a general form like this: 1 over 2 square root 0 plus minus 1 raised to power y naught 1, right? So Hadamard on a single bit y naught can be written for both possibilities of y naught like this: 0 ket plus minus 1 raised to power y naught into 1 ket. Now if y naught is 0, I will get this first state. If y naught is 1, I will get the second state. But this now gives me a tool to work with general bit state and write the Hadamard output. Actually, I can even write it like this: sum over y naught 1 over square root 2 and minus 1 power y naught into y naught. And you can check that this is equal to just this, because when y naught goes from 0 to 1, when y naught is 0, minus 1 power 0 is plus 1, and this y naught is 0, so this first state comes out. And plus, when y naught is 1, this minus 1 raised to power 1, and this is 1, so this second state comes out. And let's see, does it look okay or not? No, it doesn't, because y naught can be 0 and 1, and this is something else. So sorry, I made an error. Let's say we have a sum over some k naught going from 0, and where minus 1 raised to power is going to be k naught into y naught into k naught, because we have to make sure that the first term always is 0. So when k naught is 0, this is 0, and when k naught is 0 here, it doesn't matter what y naught is. If y naught is 0, okay, 0 into 0 is 0. If y naught is 1, then 0 into 1 is 0. So minus 1 raised to power 0 is always plus 1. So when k, for the this first term is always going to be 0. When k naught is 1, no, this one term will come here, but this k naught is 1, so minus 1 raised to power y naught, and this term will come. If y naught is 0, then this is plus, and if y naught is 1, this is minus state. Okay, so the Hadamard of a general single qubit y naught is given by this expression. So this minus 1 raised to power k naught y naught. Is everybody okay with this thing, or any repetition is needed of any part? Perfect. So if you're okay with this, let's see what happens if I have Hadamard on qubit y1 tensor with Hadamard on qubit y naught. So it means I can write this as 1 over square root 2 some k1 go from 0 to 1 minus 1 power k1 y1 k1 tensor 1 over square root 2 k naught going from 0 to 1 minus 1 power k naught y naught into k naught, and which I can combine together like this. So 1 over square root 2 and 1 over square root 2 is equal to 2 power square root, and then there is sum over k naught, there is sum over k1, and this becomes minus 1 into minus 1 raised to power k1 y1 plus k naught y1, and this is k1 k naught. So it means now this has there are two sums, and both k1 going from 0 to 1 and k naught going from 0 to 1, and where now minus 1 power k1 y1 plus k naught y naught. And you see the reason for this thing is this phase part coming in addition to this part, because if this y0 and y1 they're both zero states, then their Hadamard will give us all amplitude as positive, because this will make it 1 over square root 2 0 plus 1, and this will make it 1 over square root 2 0 plus 1, and their product will give us combination states like 0 0 0 1, and but with all plus sign, because there's a plus sign here but a plus sign here. But if this is a minus one state, then this Hadamard will give us minus sign, and the product will have again 0 0 0 1 1 0 1 1, but some signs will be negative. And this part is just giving us which terms should come with negative sign. Okay, by the way, you can write it again in a bit more condensed form. This capital N is 2 power 2, and instead of putting two sums over k0 and k1, I can define a quantity k, which is now going from 0 to actually 3 in this case, because there are a total of 3 terms. And when k is 0, it means k0 is 0, k1 is 0. When k is 1, it means k0 is 1, k1 is 0. When k is 2, it means k1 is 1 and this is 0. When k is 3, it means they're both 1 1. And then I can write here k vector dot y vector and sum over this case, where again k 0 1 2 3 has usual meaning, that k0 corresponds to 0 0, k2 corresponds to 1 0, and so on. Now you see this is k dot y, because this is nothing but looks like an inner product of y vector and k vector. Okay, so let me now generalize to n bits. If you have a Hadamard transform acting on an n bit number y, this is just equal to 1 over n square root k going from 0 to n minus 1 power k vector dot y vector into k. And this is essentially again a uniform superposition, but now with the amplitude either plus or minus. Some would be plus, some would be minus, depending exactly on this bit state y, because there's a k dot y. And if this y is 0, this term goes away, and we have usual Hadamard transform of all 0 states. Any question about this general Hadamard transform? Okay, if not, let me now get back to our output of the algorithm. So we had reached this part. So this was psi 2, and let's see what psi 3 is. So psi 3 is after second Hadamard. Psi 3 is just the second Hadamard stage applied to psi 2, and psi 2, if I rewrite, is sum over x minus 1 power f of x into x, where x goes from 0 to n minus 1. So this is n bit Hadamard transform. So this Hadamard transform goes straight to this vector state, because all of these are scalars, and scalars are right there, sum over x minus 1 power f of x. Hadamard goes to this state x, and now this thing we just wrote, that the Hadamard transform applied to a general bit state n x is given by 1 over n square root sum over k going 0 from to n minus 1 minus 1 raised to power k dot and let me now use so this is k dot x on k. So this is x, so it's k dot x. Previously the general thing that we had worked out, this has y, So it was k dot y, and sum is over k. Perfect. So now we have reached the stage where I can find the total output of this quantum algorithm just before the measurement, like this. So this 1 over n square root, 1 over n square root becomes 1 over n. Now there is a sum over x, there's a sum over k, and minus 1 raised to power f of x, this term, plus k dot x, and there's a sum over k. And let me just write it, something like this: sum over k0 to n minus 1, and combine everything else over here. And there is a sum over x here, and then there's this term. So let me put this part into a bracket, because this is, looking like something like this, that I have a final output like k0 to n minus 1 and some coefficient cl. Actually, let's call it ck, like this. That I have an output state that looks like this: c naught 0 0, c1 1, c2 0 0 0 1 0, and all the way to cn minus 1 1 1 1 1 1. And you see, we started from a stage psi naught where all 0 0 0 0 0 1 etc. all state had equal amplitude 1 over n square root. But now we have come to the final output where all of these, possible computational states, they are coming with different amplitudes in general, and those amplitude are given by this ck, where the ck is if I just write it 1 over n sum over x minus 1 power f of x plus k dot x. And let's now see what are these amplitudes. Okay, and you can compute these amplitudes for any general k that you want, but let me just compute this amplitude for this 0 0 state. So because that will give me the probability of measuring 0 0 state. Remember, the probability of measuring states is the amplitude modulus square. So probability of measuring 0 0 0 for c naught mod square, probability of measuring 0 0 1 is c1 mod square, and so on. So to find out the probability of measuring 0 0 state, I need to find this coefficient c naught. And it's important because we will see that this can tell us about the nature of this function f of x very quickly. So let's compute this coefficient c naught. So c naught is this coefficient. This is 1 over n sum over x minus 1 power f of x, because k is 0, so k dot x, that goes away, and I only have this minus 1 power f of x. And let's see what it is for the case of different types of f of x. What if f is all 0? It's a constant function, f0 for all x. So what would happen? It means this f of x is 0 for all x, x0 going from n to 1. And if this is 0, if f of x is 0, what I do have? So I have minus 1 raised to power 0, which is plus 1. So I have 1 over n sum over all 1, and sum is going from x0 to n minus 1, which is nothing but 1 over n, 1 plus 1 plus 1 n times. And this is equal to n over n equal to 1. So it means my c naught is 1 if f is 1. Now let's see what happens if f is 1. If f of x is 1 for all x, then c naught would be 1 over n, x going from 0 to 1. So this is 1. So I have this sum over -1. So this is nothing but -1 over n. I can take this minus common. Let's not even take this common. So this is -1, -1, -1 n times. And this will give me a C naught minus n over n of -1. And what's the probability of measuring? So probability of measuring all output 0 is equal to C naught mod square is equal to 1 if f of x is either 0 or 1. Because when it is 0 or 1, C naught is -1, so C -1 mod square is 1. So it means if I now measure my output and output is 0, 0, 0, I can be dead sure that the black box has implemented a function f of x that was either 0 or 1. Because if the output is 0, it has a 100% probability of coming to 0 for this constant function. And let's see what is the C naught if f of x is balanced. So C naught is 1 over n, sum x going from 0 to n minus 1 power f of x. Now, if f of x is balanced, it means for half of the values of x, it is 0. And for the other half of values of x, it's 1, which means that this sum would be sum -1, plus 1, maybe -1, plus 1, and so on. Because it is 0 for one half, and exactly for the other half, it is 1. So sometime I get -1, sometime I get +1, and this sum would cancel out, and I will have 0 over n equal to 0. And probability of measuring 0 if f of x is balanced is equal to 0. So it means if you do a measurement and you don't find output state in 0, 0, 0, it could be anything else. It could be 0, 1, 0, it could be 0, 1, 1, it doesn't matter. If it is not 0, then it's a balanced function. And you see that a quantum computer is able to solve this problem in a single query, because we access that black box only once when we pass this superposition state to this black box, and then we got the output. And you can, as see easily, I hope, that the power came from the fact that we were able to give this phase oracle a superposition state that worked on the superposition state at once and gave us an output. And then, of course, we did an what we call an interference step and increase or decrease the probability of the 0 state depending on the possible function. And with this measurement now, this result can tell us in a single run of this algorithm that whether the f of x that was implemented in this black box was a balanced or a constant function. So a problem that is exponentially hard on a classical computer can be solved efficiently on a quantum computer, and that is what sort of started a lot of work on quantum computers beginning in 1992. And that's why this algorithm is important, because it stimulated that interest in quantum computers. Any question on the Deutsch Josza algorithm?
सर आप वो probability for f is equal to 0 और 1 दिखाएंगे?
जी. So okay, let me start from here. So this is psi3 output of after the Hadamard transform. So this is essentially the coefficients of different terms in this superposition, and I just wrote these CKs over here. So this is my CK, and I was measuring the probability of finding this state K in 0 state. So K0 mean this 0 into x, so this term goes away. So essentially C0 is only this part, -1 raised to power f of x. And it's simple. If f of x is a constant function, either 0 or 1. You add same term n number of times, so you get n into either +1 or -1. So n goes with n. So C naught is 1 when f of x is 0. And when f of x is throughout 1, you get C naught as -1. So the mod square is 1. So here you have a 100% probability of finding 0 if f of x is a constant. If f of x is balanced, it means that half of the time this is 0, half of the time this is 1. So sometime all of you understand that this is, a sum, right? So you evaluate each term for each value of x, and you write these numbers and then add them. So when this is 0, you get +1. When this is 1, you get -1, and then you add them all up. And since half of them are plus, half of them minus, the addition goes to 0. Okay.
Okay, sir.
Any other question? Okay, so perfect. Now we will, study its implementation on Qiskit.